The main feature of the NICA collider, in comparison with other colliders, as I have already said, is the fact that the frequency shift due to the behavior of the bunch field is about one level higher than the frequency shift owing to the behavior of the oppositely directed bunch. If we know the major limiting factor in the formula for luminosity, we may group the parameters and clearly define the betatron frequency shift due to the behavior of the bunch field. In this way, we will discover interesting new facts. The luminosity will be proportional to the beam emittance and to the square root of the maximum acceptable frequency shift, which is inversely proportional to the square root of the circumference of the accelerator. In this sense, it is absolutely incomprehensible, say, for people who develop high-energy colliders. Generally speaking, for example, the Large Hadron Collider had an entire program for obtaining the projected luminosity by achieving the minimum achievable emittance. A whole schedule has been made of acceptable emittance growth during beam acceleration in various facilities, and a great effort has been made to achieve minimum emittance. The NICA collider should pursue the exact opposite goal. It needs to provide sufficiently large acceptance of the accelerator, namely the field of steady motion, and fill it up with particles to the fullest extent possible. Next, for high-energy colliders, the facility circumference doesn't fall within the luminosity limitation. That is why the collider circumference has been selected on the basis of the production cost of the tunnel and the convenience of accommodating detectors and other devices. The NICA collider should build a facility with the smallest possible circumference. Naturally, as any other collider, of the utmost importance is the selection of the operation point and the right choice of betatron oscillation frequencies, because luminosity is proportional to the square root of the acceptable frequency shift. What do such characteristics of luminosity lead to? The accelerator needs to be built, as I have already mentioned, with the smallest possible circumference. One needs to achieve the maximum possible beam emittance at the accelerator while obtaining maximum luminosity. With increased emittance, one must raise the number of particles so that the frequency shift remains constant. By achieving this condition, one achieves maximum luminosity. Meanwhile, it turns out that, depending on the energy on which the collider operates, the bunch intensity varies. That is why an injection chain needs to be included, which allows the bunch intensity to be varied within a wide range. Since a synchrotron is normally capable of providing only a certain maximum bunch intensity, and further varying of the intensity is only possible downwards, it is necessary to incorporate a beam accumulation scheme in the collider. The beam accumulation scheme in the collider and in the storage rings of the collider requires the application of cooling methods. These principal features, which have emerged due to the very concept of conducting a collider experiment at a very low energy level, played a determining role in the design of the structure of the NICA collider. To ensure beam stacking, a very complex RF system was required. As opposed to any other colliders, the operation of two cooling systems has been incorporated in the project: a stochastic cooling system and an electron cooling system. Without these systems, a collider can basically not operate. Cooling systems have appeared in many colliders. There are projects, for example, at the Large Hadron Collider. However, it is possible to obtain reasonable parameters on high-energy colliders without cooling systems. A key feature of our collider is the operation of the cooling systems during the process of accumulation during the experiment.